2 minutes ago, the universe got stranger again. A fresh set of James Webb observations has pulled 3I/Atlas back into the spotlight, and what those images suggest is not terrifying because this object is coming for Earth. It is terrifying because every new frame makes one fact harder to ignore. This thing was not born here. It does not behave exactly like the comets we know, and the more clearly we see it, the more it starts to look like a message from a part of the galaxy our solar system has never been able to show us on its own. For months, astronomers have been trying to answer the same question. Is 3I/Atlas just another frozen wanderer passing through, or is it one of the most important cosmic visitors ever recorded? What Webb has now revealed pushes that question into a much darker and much more fascinating place. This is the kind of story that sounds exaggerated until you slow down and look at what is actually happening. 3I/Atlas is only the third known interstellar object ever discovered moving through our solar system. That alone would be enough to make it historic. But this is not just a rare object. It is a rare object that appears to carry chemistry unlike what scientists usually see in comets from our own neighborhood. It is moving at an astonishing speed, wrapped in gas and dust that change as sunlight heats it, and every major telescope that turns toward it seems to find another reason this visitor does not fit neatly into the categories astronomers are comfortable with. The reason people are using words like terrifying is not because there is an impact threat. There is not. The reason is that 3I/Atlas is exposing how small our sample size has really been. When 3I/Atlas was first reported in July 2025 by the Atlas Survey Telescope in Chile, scientists immediately recognized that its path was the real giveaway. It was not following a closed orbit around the Sun. Its trajectory was hyperbolic, which is the technical way of saying this object was not bound to our solar system and was not going to stay. Trace its path backward, and it came from interstellar space. Trace it forward, and it leaves again. That single realization instantly transformed it from a routine comet discovery into something extraordinarily valuable. Every normal comet tells us something about our own solar system's past. An interstellar comet does something far more powerful. It gives us a physical sample, at least from a distance, of another planetary system's chemistry, another star's history, another environment, another frozen archive formed somewhere out in the Milky Way, long before human beings even knew other star systems existed. That is why the latest Webb images matter so much. James Webb is not just another camera in orbit. It is the telescope scientists use when they want to stop guessing and start measuring what ordinary images cannot reveal. Visible light can show a bright coma, a tail, a fuzzy shape, a beautiful frame. Webb goes further. It reads the chemistry in the glow. It breaks light into fingerprints. It can tell astronomers what gases are actually there, how those gases are distributed, and what those ratios imply about the place where this object formed. So when people hear that James Webb has captured new images of 3I/Atlas, they should not imagine a simple glamour shot. They should imagine evidence. They should imagine an object being cross-examined by the most powerful infrared observatory humanity has ever built. And the first truly unsettling part of this story is that 3I/Atlas still refuses to be ordinary, even under that level of scrutiny. Webb's measurements have shown that this interstellar comet is unusually rich in carbon dioxide compared with the comets most scientists are used to studying in our own solar system. That alone would have been enough to make researchers pause. But the surprises did not stop there. Webb later directly detected methane gas on 3I/Atlas, the first time methane has been directly detected on an interstellar visitor. Methane is highly volatile. It does not like to stay put when solar heat arrives. So if methane is showing up strongly, scientists have to ask why it survived long enough, where it was hidden, and what that says about the layers beneath the surface. Suddenly, this is not just a comet passing through, it is a layered time capsule opening itself under heat. That buried methane clue is one of the reasons this object has become so compelling. Scientists believe the methane may have been protected below the comet's top surface layer, sealed away from sublimation until the sun's warmth reached deeper into the icy subsurface after perihelion. In plain language, the outside of this object may have looked one way, but the interior was keeping secrets. As the comet moved closer to the sun and then away again, those secrets began to leak into space where Webb could finally detect them. That matters because it suggests 3I/Atlas is not just chemically unusual on the surface. It may have been preserving a record of the environment where it formed for billions of years. Every gas released from deeper layers is like another line from an ancient document being uncovered after a long burial. Then came another result that made the picture even stranger. Webb's near-infrared work found deuterium, heavy hydrogen, in proportions far beyond what astronomers usually measure in solar system comets. The amount was reported as roughly 30 times higher than the levels seen in the comets we know best. That is not a small difference. That is not a rounding error. That is the kind of gap that forces people to rethink the temperature, radiation environment, and chemical history of the place where 3I/Atlas originally formed. High deuterium points toward an extremely cold origin, a place where heavy water ice could form and remain preserved without being thermally reprocessed over long periods. In other words, 3I/Atlas may have spent its earliest history in a deeply frozen system, colder and chemically different from the environment that shaped most of our own comet population. And if that were not enough, Webb also found very little carbon-13 relative to carbon-12. That ratio matters because galaxies chemically mature over time. As stars are born and die generation after generation, certain isotopes become more enriched. The low carbon-13 levels in 3I/Atlas suggest that it may have formed very early in galactic history, before later generations of stars changed the chemical balance in the region where it was born. Put those clues together with the deuterium result, and researchers arrived at a possibility that sounds almost unreal. This object may have formed 10 to 12 billion years ago, during the era astronomers sometimes call cosmic noon, when star formation in the universe was at its peak. Think about what that means. This comet may predate the Sun by billions of years. That is where the emotional weight of this story really changes. We are not just talking about a rock with ice on it. We are talking about a traveler that may have formed when the Milky Way itself was younger, when our solar system did not exist, when Earth was not even a future possibility, when the ingredients that would later become oceans, continents, and life here were still part of someone else's cosmic timeline. If that sounds terrifying, it is because it should. Not in the horror movie sense, in the perspective-shattering sense. A thing older than our solar system has wandered into our neighborhood, brightened under our sun, and allowed us to inspect chemistry that may come from a completely different chapter of the galaxy's history. Now add the visual side of this. Hubble images showed 3I/Atlas embedded in a teardrop-shaped cocoon of dust flowing off its solid, icy nucleus. The comet looked soft around the edges, almost delicate. But that softness is deceptive. What Hubble really captured was a body actively shedding material into space, developing a plume and hints of a dust tail as sunlight worked on its frozen surface. The solid nucleus itself remains hard to isolate because the coma around it blurs the view. Even so, Hubble helped tighten the estimate. The nucleus is thought to be no more than about 3.5 miles across, though it could be much smaller, perhaps as little as around 1,000 feet. That uncertainty matters because it shows how difficult these objects are to pin down, even with one of the sharpest eyes humanity has ever launched. And yet, even without a perfectly resolved nucleus, the numbers remain astonishing. 3I/Atlas has been described as the fastest solar system visitor ever recorded, moving at roughly 130,000 miles per hour. That speed is not just impressive, it is revealing. It strongly suggests a long interstellar history, a body wandering through space for ages, its velocity gradually shaped by countless gravitational encounters across the galaxy. One researcher compared trying to reconstruct its exact birthplace to glimpsing a rifle bullet for 1,000th of a second, and then trying to figure out where it began its path. That is the challenge here. We can study what it is made of. We can study how it behaves under sunlight, but its original home may already be gone, transformed, or impossible to identify after billions of years of galactic motion. This is why the images matter more than the word images usually implies. The public hears that Webb has captured new views and imagines something like a sharper photo. Scientists hear the same thing and think about composition maps, gas distribution, ratios of isotopes, the changing brightness of coma features, the timing of outgassing, and the way all of that can be stitched together into a physical story. One infrared observation can reveal whether water is fading faster than methane. Another can show whether carbon dioxide is dominating the coma. Another can help infer whether volatile ices were trapped in protected layers below the surface. So when a channel title says James Webb captured terrifying new images, the strongest way to pay that off is to explain that these images are terrifying because they are loaded with chemical evidence. And that evidence keeps telling us this object was forged in conditions we barely recognize. There is another reason this visitor has become such a magnet for attention. NASA did not treat 3I/Atlas like a one-off curiosity. It launched an unprecedented system-wide observing campaign. 12 NASA assets captured and processed imagery of the comet after discovery, with different spacecraft and telescopes seeing it from different parts of the solar system. That is extraordinary. Mars orbiters looked at it. The Perseverance rover on Mars caught a faint glimpse from the ground. Sun-watching missions tracked it when Earth-based telescopes could not see near the sun. Spacecraft heading toward asteroids paused to observe it in transit. Hubble observed it. Webb observed it. SP-HIREX observed it. Parker Solar Probe, SOO, STIRO, Lucy, Psyche, Europa Clipper, MAVEN, MRO, and others all contributed pieces of the puzzle. This was not routine astronomy. This was an all-hands scientific pursuit. That kind of response tells you how rare the opportunity really is. Interstellar objects do not announce themselves years in advance with neatly planned flybys. They appear, they surprise, and then they leave. Miss the window, and the chance is gone. That urgency changes how astronomers work. Planned schedules get interrupted. Telescopes are retasked. Missions built for completely different goals suddenly become part of the same chase. Webb's observation time is among the most valuable in science, and yet astronomers were granted an interruption to use NIR spec on 3I/Atlas because the potential value was simply too high to ignore. If you want to know how important this object is, look at the behavior of the scientific community. They moved fast because they knew they were looking at something history might not give them again for a very long time. And what has all that attention shown so far? It has shown that 3I/Atlas is active like a comet, but not comfortably familiar like the comets we have cataloged for generations. Its water output dropped sharply as it moved away from the sun, which is expected for water ice because water shuts down relatively quickly as heating weakens. But methane and carbon dioxide told a more unusual story. The object kept advertising a chemistry that did not line up well with the bulk of solar system comets. Some missions saw the surrounding coma in different wavelengths. Some captured the tail. Some refined the trajectory. Others focused on ultraviolet or infrared signatures. Piece by piece, the portrait became richer and stranger at the same time. This is where smart script pacing matters, because viewers naturally ask the biggest question next. If 3I/Atlas is so strange, does that mean it is artificial? Does it mean alien technology? Does it mean scientists are hiding something? The honest answer is no. Nothing in the data requires an artificial explanation. Everything observed so far can be interpreted within the framework of a natural interstellar comet. But that does not make the object less extraordinary. In some ways, the natural explanation is more dramatic because it means the galaxy may be full of chemically diverse frozen bodies wandering between stars, and we are only now getting good enough at surveying the sky to catch them. 3I/Atlas is terrifying not because it breaks physics, but because it expands the scale of ordinary cosmic reality in a way our instincts are not built to handle. It also forces a comparison with the only other interstellar visitors we know. First came one Oumuamua, a discovery that triggered years of argument because it looked so unusual and was seen under frustratingly limited conditions. Then came 2I Borisov, which behaved more recognizably like a comet and gave astronomers a cleaner look at an interstellar body shedding material. Now comes 3I/Atlas, and this one may be the most chemically revealing yet. Instead of ending the conversation, it widens it. It says the interstellar population may not be one simple class of objects. Some may be rocky, some more comet-like, some chemically ancient, some dynamically extreme, some easier to interpret than others. With only 3 confirmed examples, every new case has outsized power. A single object can reshape the working assumptions of an entire field. That is part of what makes these newest Webb results so effective as a retention engine in a script. They are not just one more discovery. They are a pivot point in the narrative. At first, 3I/Atlas was important because it was rare. Then it became more important because it looked compositionally odd. Then it became even more important because isotopes suggested extreme age and a distant, cold birth environment. Now, the story is no longer simply that we found an interstellar comet. The story is that we may be holding, through remote observation, one of the oldest and most chemically revealing relics ever studied in our solar system. Every step up that ladder changes the viewer's sense of scale. And if you want a true rehook for the middle of the script, here it is. The terrifying thing about 3i/Atlas is not what it might do to us. It is what it might reveal about how many other worlds were built in ways profoundly different from our own. For decades, people casually assumed our solar system was a decent template for how planetary systems generally work. Then exoplanets started showing us hot Jupiters, strange orbital architectures, and systems that looked nothing like ours. Now interstellar visitors are beginning to do something similar for small bodies. They are telling us that even comets, those icy leftovers we once thought we understood fairly well, may vary more wildly from system to system than we ever imagined. That has enormous implications. Comets are not just dirty snowballs drifting through darkness. They are chemical storage vaults. They preserve clues about the disks they formed in, the radiation fields they experienced, the temperatures that shape their ices, and the ingredients that may have been available during planet formation. If 3i/Atlas really formed in a cold, dense environment 10 to 12 billion years ago, then its existence suggests that complex cometary chemistry was already happening in ancient parts of the galaxy long before the Sun formed. That pushes the story far beyond astronomy fandom. It touches the much larger question of how common the chemical building blocks of life might be across space and time. Even NASA researchers have emphasized that point. The interest is not only in the exotic isotopes. The interest is in prebiotic chemistry, in asking whether the conditions that eventually supported life here might be common or rare elsewhere. We only know one place where chemistry became biology. That is Earth. But objects like 3i/Atlas offer indirect evidence about what ingredients existed in other systems and how early those ingredients were assembled. That does not mean this comet carried life. It means the chemistry locked in its ices may help reveal how fertile or unfertile the galaxy has been for life's raw materials over immense spans of time. That is a much more powerful and intellectually honest mystery than any sensational claim about alien machinery. And yet visually, this object still earns the word terrifying in a different way. There is something unnerving about seeing a faint smudge of light and realizing it is not just another comet from the Kuiper Belt or Oort cloud. It is a traveler from outside the solar system, passing through at enormous speed, wrapped in a glowing cocoon of gas that our best telescopes are decoding in real time. The images from different missions do not merely show a point of light. They show context, a coma, a tail, sunlit outgassing, different wavelengths emphasizing different materials. They show that the object is active, dynamic, responsive to solar heating, and physically legible enough to make the unknown feel suddenly close. Space is always abstract until a frame like this makes it personal. That is also why the fleet-wide nature of the campaign matters so much for storytelling. Mars missions gave us views from a different part of the solar system. Sun-observing spacecraft caught the comet when Earth-based astronomers were effectively blinded by the Sun's position. Outbound asteroid missions collected supporting imagery from still other vantage points. Hubble sharpened the physical picture. Webb decoded the chemistry. SphereX added infrared context. Each mission saw the same visitor in a different way, from a different place, with a different instrument, producing a layered understanding no single telescope could have delivered alone. In a sense, 3i/Atlas did not just pass through our solar system. It was interrogated by a civilization-wide observing network spread across that solar system. And still, for all this progress, the object keeps some of its biggest secrets. Scientists still cannot directly see the nucleus with total clarity because the surrounding coma obscures it. They still cannot identify the exact star system it came from. They still do not know how representative it is of interstellar objects as a whole. They still cannot say whether the next visitor will resemble it at all. Those unknowns are not weaknesses in the story. They are fuel. Good long-form space content does not die when science refuses to give a final answer. It gets stronger. Viewers stay when they sense that the mystery is genuine, not manufactured. 3i/Atlas offers exactly that kind of mystery, bounded by real data, sharpened by real measurements, but still unresolved where it matters most. There is also a broader philosophical punch hidden in all this. For centuries, human beings stared at the night sky and imagined the stars as distant but separate. Then astronomy taught us that stars are suns, that planets orbit them, that chemistry is universal, that galaxies evolve, and that small bodies preserve history. 3i/Atlas ties many of those realizations together in one moving object. It is not from here, but we can still read it. It belongs to another system, yet the same laws of physics let us interpret its gases and isotopes. It is alien in origin without being incomprehensible. That balance between familiarity and otherness is what makes it so captivating. It is a foreign object written in a language the universe taught us to understand just well enough to become more curious, not less. And that curiosity cuts both ways. The more we learn about 3I/Atlas, the more it may also teach us about our own solar system by contrast. If our comets generally have lower deuterium and different carbon isotope patterns, why? If 3I/Atlas is unusually rich in carbon dioxide and carries buried methane that emerged under solar heating in a distinctive way, what does that say about the disk our sun formed from compared with the one that produced this comet? Could our solar system be chemically less typical than we once believed? Could some environments in the early galaxy have produced comet populations very different from ours? Sometimes the fastest way to understand home is to examine something that clearly did not come from home. This is why the object has become such a strong fit for channels chasing high engagement. It sits at the intersection of rarity, mystery, scale, imagery, chemistry, age, and existential perspective. It gives you fear without needing danger. It gives you science without becoming dry. It gives you real uncertainty without forcing you into nonsense. And most importantly, it gives you escalation at multiple levels. First, rare interstellar object, then active comet, then strange chemistry, then buried methane, then huge deuterium signal, then ancient origin, then possible formation during cosmic noon. That is not one hook. That is a ladder of hooks, each one higher than the last. But a strong script also needs a stabilizing paragraph where the audience is told what not to fear. 3I/Atlas does not pose a threat to Earth. Its closest approach to Earth still leaves it far away, and the excitement here is observational, not defensive. NASA's involvement supports tracking and understanding, but this is not a planetary emergency story. Clarifying that is important because it allows the real tension to breathe. The terror is intellectual. The terror is that the universe can send us an ancient fragment from another system, and in the process remind us that our textbooks were built from a tiny sample of local objects. Once that idea lands, the story stops being about one comet and starts being about how much of the galaxy remains chemically unfamiliar to us. So, when people ask what is so terrifying about these new Webb images, the answer is this. They are terrifying because they show that 3I/Atlas is not simply a visitor from another place. It is a visitor from another time, another chemical environment, possibly another era of galactic history. It carries evidence of deep cold, unusual isotopic ratios, high carbon dioxide output, and methane released from hidden layers after solar heating. It may have formed billions of years before the sun. It may have wandered the galaxy for ages before intersecting our path. And now, for a brief moment, we are close enough and capable enough to read some of that history before the object disappears again into interstellar darkness. That is the emotional center of the entire script. Human civilization built telescopes powerful enough to catch a frozen relic from another stellar system in the act of shedding ancient gases under our sun. We did not make it. We did not summon it. We barely had enough warning to turn the full network toward it. And yet there it is, offering chemistry, motion, age clues, and perspective in equal measure. Most objects we study belong to the family we grew up in. 3I/Atlas does not. It is the astronomical equivalent of a stranger opening a suitcase in front of us and revealing artifacts from a civilization we never visited, a climate we never lived in, and a time before our own world existed. The final thing viewers should understand is that this story is not over just because the object is receding. Interstellar science works differently from ordinary breaking news. The images come first, then the deeper analysis, then the arguments, then the refined models, then the comparisons with solar system comets, then the broader implications. Webb's results will keep echoing through papers and debates long after 3I/Atlas is too far away for new observations to matter. Scientists will ask whether its chemistry really is as extreme as it appears, whether its age estimate can be tightened, whether its isotopic signatures point to one kind of environment or several possibilities, and what lessons it offers for the next interstellar object we manage to catch. In that sense, the terrifying part is just beginning. Because once you know something like 3I/Atlas exists, the universe does not go back to feeling smaller. You cannot unlearn that an ancient interstellar comet may have crossed into our solar system carrying chemistry from a frozen environment formed 10 to 12 billion years ago. You cannot unsee the fact that one object can force major observatories and spacecraft across the solar system into a coordinated chase. And you cannot easily return to the comforting idea that our local comets are an adequate template for everything else that drifts between the stars. The new Webb images do more than show a comet. They widen the map of what counts as normal in the galaxy, and they do it in a way that leaves our own solar system feeling less central than it did before. So if you want the cleanest possible conclusion, it is this. 3I/Atlas is not terrifying because it is coming to destroy us. It is terrifying because it is real, ancient, measurable, and foreign in the most scientifically meaningful way. Its hyperbolic path proves it came from beyond our solar system. Hubble shows an active, dust-shrouded body with a still uncertain nucleus size. Webb reveals methane, carbon dioxide, strange isotopic fingerprints, and clues pointing to a deeply frozen origin that may reach back to cosmic noon. NASA's entire observing network has treated it like a once-in-a-generation opportunity, and every fresh look suggests the same thing. This may be one of the oldest, strangest, and most revealing cosmic visitors humanity has ever studied. The universe did not send us a monster. It sent us a witness from another system, perhaps from another age of the Milky Way, carrying in its ice the record of conditions we have never directly sampled before. James Webb's new images are terrifying because they make that witness harder to dismiss as just another point of light. They turn it into evidence that planetary systems can freeze chemistry into small bodies and then scatter those bodies across interstellar space for billions of years. Evidence that our own solar system may be only one version of a much larger story. Evidence that every time we improve our instruments, the cosmos responds by showing us something older, stranger, and more humbling than we were prepared to see. And 3, I/Atlas may be the clearest warning yet that the galaxy has been writing histories long before we were around to read them.